This video discusses the labor discipline model. The labor discipline model models how employers interact with workers as a two-stage game, that is, with two players being the employer and the worker. In the first stage of the game, the employer chooses the wage, while in the second stage of the game, the worker chooses their work effort. The employer sets the wage to, firstly, acquire the effort at the lowest possible cost, and secondly, maximize profits subject to the worker's best response function. On the other hand, the worker puts in a level of effort that balances the benefits of keeping her job and as a consequence employment rent and also the cost due to the disutility of effort. Therefore, the model describes the wage, effort, profit, and employment rent at the Nash equilibrium, that is, at an equilibrium where players are doing what's in their best interest. Let's look at an example. Suppose Homer dislikes working at the local nuclear power plant, but he needs the money, so he works 40 hours a week. If he were fired, he would receive unemployment benefits of $5 an hour. In this case, Homer's reservation wage is the value of his unemployment benefits, that is, the $5 per hour, because at that wage, he is indifferent between working and not working. Basically, he has no incentive to work for less than $5 per hour if he would get the same amount by not doing anything. Homer's best response function can be shown in a graph to indicate how much effort to put into his work, with 0 being no effort and 1 being perfect effort, that is the maximum possible effort. On the x-axis, we have hourly wages, while on the y-axis, we have effort per hour. Graphing the worker's best response function would depend on the reservation wage. In our case, we have $5 per hour, and that's where the worker's best response function would start from. So if it's graphed, it would look something like this, where the graph would be the worker's best response function when expected unemployment duration is 44 weeks, and the area under the graph would be the feasible set. There are two characteristics that we can note from this graph, and the first is that the worker's best response function has a positive slope because the worker will always put in more effort if he's paid a higher wage, and the second characteristic is that it's concave because as his wages increases, each additional dollar has a smaller impact on his effort level. Looking at the characteristics of the worker's best response function or the feasible frontier in a different way, we can firstly say that the slope of the worker's best response function is the employer's marginal rate of transformation of wages into effort. And secondly, the concave nature of the worker's best response function shows that as wages increase or as we move to the right from the left of the x-axis, the slope becomes smaller and smaller, signifying diminishing marginal returns for the worker. From the employer's point of view, firms' strategy is to search for a feasible combination of effort and wage that minimizes the cost per unit of effort or minimizes W divided by E. Saying the same thing in a different way, firms seek a feasible wage-effort combination with the highest possible effort per dollar, or simply the reciprocal of what we defined earlier. Isocost curves show all the effort and wage combinations that generate the same profit for the firm. To the employer, this isocost line is simply his indifference curve. The slope of the isocost line is the marginal rate of substitution, which is the rate at which the employer is willing to increase wages to get higher effort. Different isocost lines can be drawn to reflect different cost levels. Of the three isocost lines drawn in the graph, X has the lowest cost while Z has the highest cost. However, a firm would not pick X or Z because X is outside the feasible frontier, that is, it's infeasible, while Z is feasible but it has a higher cost compared to Y. Therefore, a firm would pick a wage effort combination on the Y isocost line relative to the others. Now, assuming that Mr. Burns knows Homer's best response function, what wage will he offer Homer? Will Homer accept that wage? If so, how much effort will Homer put in on the job? Given their best response function on the right, which may be drawn differently by different people, Mr. Burns would pay Homer a wage of $11 per hour. At this wage, Mr. Burns' isoprofit line is tangent to Homer's best response curve. Since this is the highest feasible isoprofit line for Mr. Burns, $11 per hour represents the profit maximizing wage. This is simply the efficiency wage, that is, the wage at which the marginal rate of transformation is equal to marginal rate of substitution. Note that any other wage would lead Mr. Burns to extract less effort out of Homer for each dollar spent. Homer will accept any offer greater than his reservation wage of $5, and at $11 per hour, he will put in an effort of 0.6 as shown in the graph. Suppose that at the equilibrium found earlier, Homer experiences a disutility of effort of $1 an hour, and that if he were fired, he would be unemployed for 26 weeks until he found another job with the same wage and disutility of work as a job at a nuclear power plant. In this case, the employment rent can be found in the following way. If Homer earns a wage of $11 and experiences a disutility of $1 an hour, each hour of work is gaining him $10 in utility per hour. This can be illustrated in the graph as follows. On the x-axis, we have number of 35-hour weeks, while on the y-axis, we have wages and disutility of effort. What Homer gets should he not lose his job today is shown by the blue line. The unemployment benefits plus disutility of effort is equal to $6. The unemployment benefits or the reservation wage, which is $5, is simply what Homer gets should he lose his job today. Therefore, the reservation wage is represented by the orange rectangle. The gap between the reservation wage, which is $5, and his current utility, which is $10 per hour, is $5 per hour. Homer's rent, when employed, that is employment rent per hour, is represented by the blue rectangle. Therefore, in terms of calculations, if he lost his job for 26 weeks, he would be losing $5 an hour for 40 hours a week for 26 weeks, which is the same as $5 multiplied by 40 multiplied by 26, which gives us $5,200, and this is the value of Homer's employment rent. Let's now switch gears. Suppose that the financial system collapses, the economy slides into a recession, the unemployment rate doubles, and by implication, it would now take 52 weeks for Homer to find a new job. What would be the employment rent in this new scenario? Employment rent in this particular case would be calculated in a similar fashion. If he lost his job for 52 weeks instead of the 26 weeks that we were looking at before, he would be losing $5 an hour for 40 hours a week for 26 weeks, which equals $5 multiplied by 40 multiplied by 52, giving us $10,400 as employment rent. But what happens to the how do we illustrate this in a graph? Graphically, you'd expect a recession to cause Homer's best response function to shift upwards. However, the shift does not change the reservation wage since he could still receive $5 an hour in unemployment benefits. Finally, what does this model suggest and what does the evidence tell us? This model suggests that this will lead to a lower wage and higher effort, while evidence does suggest that workers work harder in periods of higher employment. Very few employers cut wages. This model inconsistency suggests that our model may abstract from an important aspect of the labor market.